in this department, we don't need much of introduction on the kind of issues that we face around water, in particular in Canada. Of course, almost every other year, we get a major flood somewhere in the country. And of course, Vancouver and November last year flooding, still the memory is still very, very fresh. Extreme wildfires, of course, you always have very fresh memories of that. And you now know that extreme wildfires in just past summer intensified significantly a lot of flooding events, and basically roads being washing away, because basically when the land surface is burned, you get impermeable baked land surface. And of course, there is no interception by trees, so pretty much the whatever rains transfers to runoff and flood. Again, drought might so drought in BC might not be as evident as it is in central Canada, in the Prairie region. So anyways, it's a big issue if we've had major floods in Canada. And you know what, when people think of Canada, you always think Canada is the water country in Canada and elsewhere. But you know what, it's not necessarily the case. If you live in BC always, yeah, you might get that impression, but just travel to central Canada. And there is a lot of water-stressed regions. There is a lot of water security issues, both in terms of quantity and quality. So anyway, that's a big one. Water quality, of course, in particular northern communities. Of course, global warming, no need to say. For example, our winters have been warming. So just in the past 30, 40 years, we lost a lot of our coldness in wintertime, more than 6 degrees Celsius. And you know what, you just need to live in Saskatoon for 10 years like me. Just over the period of 10 years, you feel like, oh, winters are getting better and better, more tolerable. But you know what, the change in summer is not at least as evident. And you know, when you look at statistics, that's the case. Permafrost, of course, when you go further to the north, and that is where I'm going to present some about, of course, all sort of issues because of warming. We're going to get there. So permafrost thaw, compaction of soil, landscape connectivity, changes in hydrology regime, and so on. And glacial retreat. Again, glaciers, in particular for the prairie, is a major source of water. In the glaciers in the Rockies have been estimated to provide somewhere around 40–50% of water in Saskatchewan River in August, September. So, and that is the time that irrigation is still quite needy of that water. And we've lost a lot of glaciers. And you know what, when they're gone, then they're gone. And there's going to be some major water security issues. And you know what, glacier melt might not seem big compared to the total water we have, but it comes at the right time for irrigation, so we don't have a substitute for that when it's gone. So with that kind of introduction, this has been our kind of grand vision around integration and convergence. And basically, as you know, scientific development historically has been based on this reductionism approach, Fraser principle of parsimony. And we, as scientists, we always want to narrow down to a lower dimensional problem, something we can easily measure and work on and understand and model and so on. So that has been our guiding principle over the history of scientific developments. But now we are at the point that we understand we have to perhaps zoom out and take a more holistic approach. And this recognition has been there at least for the past 10 years quite extensively. For example, NSF, they have a big funding stream for convergence research. So they want to bring different disciplines together. And we have been trying to do so as well by bringing together the sciences of atmospheric science, hydrology, water resources systems, modeling and engineering, basically full caliber hydroeconomic modeling, social aspects, and now, as you know, very important, indigenous knowledge. And you know what, I'm going to be talking about this piece in particular because I've been focusing in particular in bringing these two, and I'm not an economist at all, but I'm going to tell you how naive people like me from engineering background could be around economy, because many of us take engineering economics in undergrad and think, okay, you understand economy, but then you realize that is all accounting and economics, the science really well beyond those things. So in this presentation, I can't cover everything, but I'm going to give you some taste of pieces of integration and what we have been doing in the past 5-6 years or so. So I'm a civil engineer by training, and my primary research is around hydrology and hydrologic modeling. So this is the school that I'm coming from. And as you know, many of us do that. Many of us do hydrologic modeling from small to large scales. And we look at all sorts of ground-based data. Now we look at all sorts of satellite data. We try to constrain our hydrologic models, better process representation, and so on, looking at different hydroclimatic variables. And typically the outcome is things like, for example, we want to estimate runoff for flood prediction or drought prediction. We want to estimate evapotranspiration, water balance, and so on. And in general, as a community, we've been doing well, but there's a but there. And that but is about an issue that we've been facing in particular in the last 10-20 years, increasingly, and that is basically non-stationarity in climate and hydrology. So we've already seen that our frequency analysis, for example, of floods in the past may not be any good for the future. So now we've built our models based on the past history, past observation, and we need to run those models in extrapolation. So we are pushing our models to predict well beyond the data used to constrain those models. And that is a big, big issue. And the thing is, there is no way to verify our predictions, because we just need to wait for another 20-30 years and see, okay, what would the impact of warming, for example, on landscape and hydrology, and then we can go back and verify our models. So we have big, big issues in hydrology. And basically, we are fairly limited in what we can do other than trying to understand the processes, physics behind all the changes that might happen, and try to build those into models. And this is something that has been partly ignored in the community. Canadian community, hydrology community, I would say, has been, to me at least, perhaps because I'm from Canada, but so we've been doing fairly well. But when you do this presentation elsewhere, you get, still there's a lot of methods just based on empirical relationships they develop without proper solid understanding of the underlying processes. To give you some context by what I mean by understanding physical processes, let's bring you to Canadian hydrology. And as you know, we live in cold regions, Canada, and you already might know that our warming rate is quite high. So when you compare the warming rate of Canada with the rest of the world, our rate is about twice as large as the global average. So we are warming twice their global average. And when you get further to the north, like in the Arctic, permafrost region is about 3 times faster than the rest of the world. So we have a big issue about warming. And that's not only that. The other issue that we have is evident in this plot. What is it? We're looking at temperature, degrees Celsius, different months, and this is the average temperature for different months for the city of Saskatchewan. And this is what I have experienced. So, and as you see, about half of the year, the temperature is below 0 degrees Celsius. And of course, you guys are lucky here in Vancouver. You don't have to experience these pieces. But the point is, temperature in Canada, most of Canada, almost all, hovers around 0 degrees Celsius. And that is when phase change happens. So there is a lot of physics exactly happening around that that range. And just compare that, for example, with PEGs. Quite not, it doesn't get below 0 really. So let's see the impact of warming on this. So of course we have this freeze thaw timing, nothing happening in Europe. And now under future climate, what happens? Things are going to be pushed up. So now we're going to have longer summers. The timing of thaw is going to happen earlier. Timing of freezing is going to happen later. Not only this has significant impact on our precipitation partitioning, we're going to get less snow, more rainfall. It's going to have major impact on our landscapes. So what this tells me, and you don't see any impact here. So what this tells me is that energy is quite tied to energy and to water balance in Canada. So we cannot ignore these shifts in hydrology. So there's going to be impact on hydrology. How can we understand that? How can we model that? So that's why many Canadian hydrologists try to simulate water and energy balance together. And that's the only way really to represent these changes, right? So with that, let me take you further north, the permafrost region. So what I just showed has significant impact on the hydrology of even southern Canada, like Saskatchewan River Basin that I've been working on extensively. But those issues get worse. And I'm going to show you some results. So what you're looking at is the vertical cross-section of the land surface. So this is my ground surface. I just go down, and here you see soil temperature. This is my 0 degrees Celsius. So if it goes below, things are frozen and thaw on the other side. And of course, so this is my envelope for temperature profile. And you have seasonality, right? Summertime, things get warm, wintertime gets cold. So my temperature profile fluctuates like this seasonally. And we have permafrost. And if you don't know what permafrost is, this is my permafrost layer. It's the land that remains frozen all year round. According to definition, more than 2 years. So anyway, so when you go up to the north, then if you dig a little bit, you get to the permafrost, you get to the basically frozen soil. And what is this area, this depth thickness? This is active layer thickness. So this is the only hydrologically active region. So this surface can kind of act like bedrock, because things are frozen, water cannot penetrate. So you can, in modeling, you can think of it in terms of process representation like just a solid bedrock, right? But what happens when you warm up? So the envelope is working like this. Gradually, the envelope will shift under a warmer climate. The active layer thickness begins widening. So you're going to have deeper active layer thickness, deeper dynamic storage. So this will have multiple major implications. Of course, the very first one is, as soon as you basically extend this, you're going to see soil compaction. As a result, you're going to see land subsidence. And that's about the photo that I showed at the beginning. So our roads are in danger, our infrastructure is in danger, hospitals, airports. So land subsidence could be quite costly. On top of that, as you know, so when you lose permafrost, it will release methane that has a positive impact on the warming itself. And on top of that, it's going to change the landscapes, and it's going to change lateral connectivity between plots of soil, for example, and it's going to change my hydrologic regime. So we need to understand that. just to show you some results on what might happen in the future, I'm going to show you the results for Liard River Basin here, which is a relatively small basin compared to our permafrost extent. And if you don't know, about half of Canada, 50% of Canadian landmass is permafrost. So it's quite big. Of course, we don't see it here in the south, but it's a treasure for Canada in general. And this particular basin is it's representative of very sensitive permafrost regions in the north. So if you zoom in, this is the general permafrost classification for this particular basin. In some areas, we have a sporadic permafrost, and this continues, and here continues. And basically, so here means you get solid permafrost, then things begin getting patchy a little bit. So this is, because of this is one of the most sensitive areas to warming. And let's see what happens in the future. So what I'm showing you, so we developed physically based hydrology land surface models for this basin, and we've simulated based on water and energy balance what's going to happen to it to the end of the century. And of course, we have a lot of uncertainty around the status quo, where we are, because there is a very limited measurements of permafrost in the north, but we don't have a good handle of what's going on at the moment even. And because of that, you see that we have developed 5 different model configurations, and each model is even telling us something different about the status quo. And then we simulate under 10 different air system models. And what I'm showing is under a very optimistic emission scenario. So the uncertainty you see at the beginning, this is the uncertainty due to land surface model parameterization. The uncertainty you see at the end here is due to climate model parameterization. So there is, of course, big uncertainty about what's going to happen, but there is a very strong signal here that even under a very optimistic emission scenario, it's possible that we lose almost entirely the permafrost base, and that basin is about 300,000 square kilometers, very big. And so when we are beginning, so this area is about 30 to 50% of the basin itself. 30 to 50% of that basin is permafrost. It can get quite close to zero, or at least to half of what we have now. So it is warning. And when we look at a pessimistic emission scenario, of course, things get worse. So yeah, if business as usual emission scenario, for example, continues, then pretty much most models converge to very small values. And then, what about the compound impacts of warmer and wetter climate? So when we talk about climate change in Canada in particular, we mostly talk about warming. But we, of course, know that precipitation regime is changing as well. So, and there is this general impression or conception or misconception, I would say, in Canada that we are wetting. So we're going to get more water. And I'm going to talk about that in a couple of minutes. But the point of this slide is that, okay, so I just discussed that energy balance and water balance are closely tied together. So do we need to look at the individual impact of warming and wetting and the compound impact? Of course, yes. So we have to separate those to tease out exactly what's going to happen. And with these type of models, of course, we can do it. So I'm showing the projection of one model here under 4 different scenarios. Just look at the first one here. So this is the future of permafrost under a mild change scenario, just 2 degrees warmer and 5% wetter. So we'll get here. And then the green one, so temperature remains the same, but from 5% increase in precipitation, we're going to go to 20% increase in precipitation. So from here to here, no more warming, just more precipitation. We're going to lose permafrost more. And why is that? So all of it boils down to snow insulation effect of the land surface. So when we get more precipitation, from 5% to 20% more precipitation, of course, the majority of it will remain as snow because still the region is quite cold. So my land surface is going to be covered by snow for longer period of time and perhaps with denser snowpacks. And snow always has insulation effect for the ground surface. So in winter time, you get lots of snow. That's just a blanket you put on the land surface. And in winter time, it doesn't let the land to basically to lose heat. So land remains warm even in very cold winters. So gradually, land surface basically loses its cold. Basically, doesn't release its heat, and because of that, you will lose more permafrost. And this could be counterintuitive to many because then if you get more snow, you feel like it's gonna be colder. And the blue one is the impact of a warmer climate event, so from 2 degrees to 4, but precipitation remains the same as the first one. Of course, warming has larger impact than wetting. I think makes sense. And when you both warm and wet, then you can see the compound impact. So it tells us that we really need to understand what's going to happen to our precipitation in addition to temperature. And that is where the biggest uncertainty lies, as I'm going to show you, I think, in the next slide. And this is the distribution of active layer thickness. I mean, the same sort of signal you could see, no need to spend time on it. And about hydrology and hydrographs, again, so when you have that model, it simulates the streamflows in the rivers as well. And in general, in the north, we're going to see more water and basically a change in peak time. So we're going to get earlier freshets and basically earlier peak times. But this is where we have still big uncertainty in our models because there is no proper physics into any available land surface model. So basically what's happening is in the north, because of this permafrost top, the landscape is changing. Just think of that image for land subsidence in the north. When that happens, lateral connectivity of soil might change. For example, water flowing in this direction, I'm talking small scale. After that land subsidence, it might be flowing another direction. So even the land surface at short time scales might change. And that can have big impacts on the hydrology. Our current generation of models cannot simulate that. And you know, for multiple reasons, of course, it's a very heterogeneous environment and almost zero data on what might happen. But who knows, in the next 5-10 years, you might see newer models that can tell us something about those kind of signals. So this is just some estimate, but very rough because we have kind of unsupported assumptions in the model about lateral connectivity. Okay, so I just said precipitation is very important, almost as much important as changes in temperature is. But we have big issues in Canada about precipitation. So what I'm going to show you is full synthesis of all semi-5 climate projections about Canada. So what you see, for example, the Rocky Mountain and in BC, for example, changes in precipitation on the annual scale. But this is the kind of trend we expect to see, and this is the range of uncertainty. For example, some models are telling us that we might get as high as 10% less precipitation to as high as about 13% more precipitation. So we have big uncertainty range from -10 to +13 just in this region on the annual scale. When you go to the north, just like in the Yukon, for example, pretty much every model tells us that okay, we're going to get more precipitation, and as high as about 35% or so. In the prairie, again, it's heavily upward, so there's still possibility of getting negative values, but they are dominantly positive. And in Ontario, Southern Ontario, similar. So this type of analysis has been a primary driver for policymaking in Canada in the past 10 years or so, in particular in the agricultural field. So when you look at this, for example, some farming communities are quite happy about this. Why? So Canada is getting warmer. Tree lines are shifting northward, so you're going to get more land to cultivate. And what else do you need? So you need land, energy, and water, right? So it's getting warmer, and it just showed longer warming season, so you can have longer cropping seasons, perhaps more than one crop season. And you're going to have more water. You have everything you need for agriculture. But there's something missing here. And I should say, what has also kind of supported this hypothesis about the future is our CAN ESM model, Canadian Air System model that is quite consistent with this signal. So let's look at seasonal changes in the future. So I'm now just breaking this down into changes in winter precipitation and changes in summer precipitation. So you'll see generally, you're going to see, yes, so the increase that we see on the annual scale pretty much comes from our increases in winter precipitation amounts. Summer, for example, in the prairie, there is big likelihood that we're going to get less precipitation. Again, perhaps just in the north, it's more biased for the positive side, but elsewhere, there are risks. And again, why is it important? Because, for example, in Saskatchewan, food basket of Canada, 97-98% of agriculture is dryland agriculture, no irrigation. So they just look at the sky, waiting for rain in summertime. So if we get less precipitation in summer, they're going to suffer. Perhaps similar in the Okanagan Valley. So this is very important, and the uncertainty range is too big. So if you present your decision maker with this type of uncertainty ranges, it creates decision paralysis. They can't make a decision. The first reaction might be, okay, you don't know your job. So they want us as analysts, engineers, scientists to come up with some design numbers for them, but this doesn't help. So basically, we are living with deep uncertainty. And we need to prepare for that, and not only on the science side, also on the policy side. So you need to educate your policymaker about the uncertainty and find a common language to basically help them in the decision process. And believe me, so I'm coming from engineering, basically a school of thought, and I've been working in private consultants for some time. You know, but quite often in practice, you end up ignoring some uncertainty. And because you have to come up with some design numbers and move on. And I mean, that could be quite risky sometimes. So we need to build our methods to accommodate for living that uncertainty. And how can we manage that? Of course, traditionally, historically, we've been relying on structural measures. Of course, now we try to also heavily emphasize on non-structural measures. You've seen a lot of nature-based solutions everywhere, in Europe in particular. Now it's coming to Canada as well. So to do these things, you need to have a model to represent human interventions to the natural process and water management in general. What I'm showing you is our water resources systems model for the Saskatchewan River Basin. So this basin has an area of about 400,000 square kilometers. That's very big. That's half the size of France. And it is heavily regulated. And this is something people typically don't know, people who don't live in the area. More than 50 reservoirs have been built on that system. So you might know, for example, many of you might have been to Banff. So that's Bull River, one of the main tributaries of South Saskatchewan River. We have North Saskatchewan River flowing to Edmonton as well. They cross the border from Alberta to Saskatchewan. Saskatchewan is here, and then they join, and then they end up in Saskatchewan River Delta and Lake Winnipeg at the end. And water allocation is quite complex in this basin. Each province has its own water licensing system. And there are transboundary water agreements between the provinces and also between Canada and the US. It's a very complex system, and the only way to get a handle on it is to develop, to build all that knowledge available into a model so you can simulate different scenarios. You can see what's going to be the impact of policy from here, or, for example, in some other place. And water management, water policy has been severely fragmented in Canada and in this region, both vertically and horizontally. So basically the mandate of Alberta, or Alberta Environments and Parks, is to look after water in Alberta. Saskatchewan Water Agency to do it in Saskatchewan, and so on. Of course, there is always communications between this, but limited within the realm of that master agreement on a portion. That is very, very high level. So there hasn't been any platform to simulate and to help promote the dialogue around water issues and policies here and there. And water, I should add, water is over-allocated in Alberta. So they have already given licenses beyond their capacity, water yield. Saskatchewan is still under-allocated. And again, to add another layer of complexity, South Saskatchewan River has major issues on over-allocation. North Saskatchewan, there's still a lot of extra water to allocate. Of course, it gets colder and less irrigation has been implemented there. But there has been a lot of talks to divert, for example, water from the north to south. So there are a lot of policy options. And you need to have a model to simulate the system to understand the implications. So now with this model, we've been able to look at trade-offs, run different policy scenarios, and see the impact of a decision here, there, or here, there. And you know what, I'm going to show you. So because in water community, we always think that whatever we do upstream will have an impact on downstream. And whatever we do downstream stays downstream, doesn't flow upward, uphill. But I'm going to show you that it can very easily. So that brings me to economic modeling side. So we basically integrated an economic model based on input-output tables with our water resources systems model. So historically, hydroeconomic modeling in engineering has been based on only direct water using segments. And that is what I referred to at the beginning, that I thought initially understand hydroeconomy. But then after beginning collaboration with my economist, Roy Brower from University of Waterloo, I realized, wow, okay, he has a point that we are missing a big part of economy. And that is, for example, the fact that just in Alberta, Saskatchewan, only 30% of the economic sectors are directly connected to water. But the rest of the economic sector is also indirectly connected to water, and that is something that we've been missing. So this is based on intersectoral, interregional transactions. So we need a system, a modeling system, in which both water and money flow, not only water. So we developed this, but I'm going to show you just small results from an analysis for just one policy option. And you might have heard of this big controversial plan in Saskatchewan to invest $4 billion to expand irrigation, just around defendator. So there has been a lot of talks, a lot of problems, a lot of consultations around this. But just let's see what would be the impact of that on just the economy itself. So we're going to see the impact of it in terms of increase in annual gross outputs in million Canadian dollars based on 2015 prices. So this way we can directly connect local scale water decisions to the GDP of each province, for example, or even the nation. So, of course, by that investment, we are going to see big contributions to irrigated crop and animal production locally. Makes sense. And of course, big contribution to manufacturing, food processing units, but also contributions to, for example, transportation and warehousing, of course, related to food again, it makes sense. But even contributions to information and cultural industries, for example, that is something that we always ignore. So there's a lot of sectors that are connected to whatever you do economically. They might benefit or they might lose something. And then you go upstream to Alberta. For example, you're going to see a big contribution to manufacturing in Alberta. So that is, so money flows upstream, right? And that makes sense because then you have more crops. There is a lot of food processing units in Alberta to process them. And even again, information and cultural industries. And this list is very big. I'm just showing you some samples. And now this way you can quantify those. So just moving on to show a piece on this socio-hydrology model. So far I've been talking about the water supply and changes in water supply. But what about the demand side? The demand is also, of course, very important. We have to do demand management as well, right? And there has been a lot going on everywhere and in Canada. So the example I'm showing is, for example, in Western Canada, Prairie region in particular, there has been some policy incentivizing improving irrigation efficiency. So people have been switching to higher efficiency systems. And what happens when they do that? A lot of interesting dynamics might emerge in farming communities about their response to policy, to climate change, whatever. So this is the type of model that agent-based model that developed for this. And the reason was to understand the possibility of rebound phenomenon, called J1 products in economics. And basically, so you have big water demand. By some policy change, you reduce the water demand. But after some point, demand might rebound. Why is it happening in agricultural sector? And it has been seen elsewhere in the world as well. So as a farmer, you use less water. You say, oh, I have extra water. Why not, for example, switching to another more water demanding crop? Or why not cultivating some extra land? So overall, if you don't monitor this in your policy making, these kind of situations might happen. And our case study was in Bow River in Alberta. Another thing that, for example, we could look at, and this is with the indigenous knowledge, looking at individual and compound impact of climate and policy change. So you might know that there is this Saskatchewan River Delta here at the almost outlet of the Saskatchewan River Basin. How many of you have heard of Saskatchewan River Delta? Just 2, 3. Interesting. You know what? So Saskatchewan River Delta, of course, located in northern Saskatchewan, is the largest inland delta in North America. According to biologists, ecologists, this is the most important source of biodiversity in the continent. But it has been ignored big time, even by people of Saskatchewan. And people even don't know it in Canada. And what has happened? And you know what? To get there, it's not easy. So you have to drive for about 6-7 hours from Saskatoon. And the last 2 hours going to be on a dirt road. And not many people living there, primarily indigenous communities. But you can ask wealthy American hunters, they fly all over from the south, they might pay as high as $30,000, $40,000 to hunt a bear. And if you go there, there are very good lodges in the middle of nowhere, basically, to host them. And that's the only touristic attraction and main source of revenue for many people. Anyway, so what we have done to this delta is big. It has major environmental issues now. And what I'm showing you is flows at Saskatchewan River Delta, seasonality, and we'll just compare the solid blue with solid red lines. This is the previous regime, and this is the current regime. So we have reduced the peak flows on average to less than a half, and we have increased almost 3 times in the low flow times. And when you look at the range of variability, the dashed lines, just see. So this has had huge impact on the ecosystem. And of course, indigenous communities living there were voiceless until just some time ago, but now they're stepping up. So now we are hearing the issues, and my colleagues and myself, we've paid frequent visits to them. They come to university, and we are trying to figure this out and using their knowledge, their history, their stories, to understand what has been the cultural flows, what is needed for ecosystem, and anyways, and see if we can do anything by better water management. But the answer, at least so far, is that with the status quo and status quo policy changes, we may not be able to help much. So this plot actually has a lot of information on it. So again, this is the same flow versus time, and the dashed red is the naturalized flows. And the base climate scenario, this one, is our simulations assuming past climate will repeat in the future, and the envelope that you see are different policy options being discussed in the region's policy discourse. Doing this, doing that. So we've collected these policy options. For example, what if we improve irrigation efficiency? What if we switch our crop mix to something less water demanding? So with all those policy options being discussed, the help is going to be very limited. And of course, climate itself is very uncertain. If you're lucky, and in the future we get, and these are based on, again, the input of climate hydrology models that I showed at the beginning. If you're lucky and get this climate scenario, this is very wet, both in South Saskatchewan River. Sorry. So anyway, so this is for a wet scenario for both in both South Saskatchewan River and North Saskatchewan River. If this happens, just because God wanted it to be like that, we can somehow recover. But again, under that scenario, the impact of our current policy discourse is going to be limited. And if we are unlucky, this climate scenario, even the situation is going to get worse. So anyway, so this has a very important message that if we want to change anything, the ecosystem, we need to find more aggressive solutions or changes to our policy. So what I showed is part of, thanks Adam for the good introduction. So part of what we've been doing under integrated modeling program for Canada, under 4 themes, looking at natural systems, human systems, decision-making under uncertainty, and user engagement. So a fairly big group of us from 4 universities have been working on this in the past 6 years already. And we have a website with all the reports and papers and whatever we have done so far. So I have a couple of more slides that I'm going to very briefly say. Role of data science and machine learning. This is something big topic on itself. So this needs basically a separate seminar at some point. But anyway, so this is where we are headed now, not trusting machine learning at all, but trying to co-evolve our process-based modeling with machine learning. So we are building a research program now around this really. And I have my skepticism around machine learning in general, but trying to figure out ways to really absorb those big data resources coming in and basically expand the knowledge base. And the last thing, data science and sensitivity analysis. So this is a good data science tools to understand what's happening in geospatial data and models in general, and it basically tells us what controls your system. And that's very important when we have big data sources and under that convergence notion. Anyway, so we've been working, as Adam said again, so developed VARS tool, which is a package now in both software package both in MATLAB and Python, with a lot of new features for sensitivity and uncertainty analysis, with multiple tutorials and educational videos. If you had interest, you could have a look. And that's it. So I had created this YouTube page a couple of years ago and trying to make some videos explaining what I'm talking about. And for example, on sensitivity analysis that I just said, and also machine learning and in hydrology. And yeah, feel free to have a look. Thank you very much.